for a critical value to be a relative extrema and a point of inflection at the same time. Most commonly, it will be one and not the other. And so you'll probably see a sign change for one of those, either the first derivative or the second derivative, but probably not both when x is positive 3. All right, so I'm going to make a table in order to help me examine the information I've collected. So my points of interest, I think that there's something interesting happening when x is negative 3 and when x is negative 1 and when x is positive 3. And so I want to make sure and break up the number line. There are no domain restrictions here, so I'll break up the number line into 4 portions around those values. And I'm going to check the sign of the first and second derivatives and find out what information I can get from that. Remember, all we care about is the sign. So don't get too caught up in like trying to remember the number. We don't care about the number. All we care about is the sign. In fact, this first derivative might be more useful to be written like this. Because since this has a power of 2, this portion will always be positive. So a positive won't change the sign when you multiply it by something else. So really, all I really care about is the sign of this factor, because it'll be multiplied by something that's always positive. So if I look at the sign of that green factor, I'm going to be able to figure out the sign on any interval. So in the interval from negative infinity to negative 3, I'll pick like negative 5. And I'll get a negative output, which tells me I am decreasing for f on that interval. On the other side of negative 3, if I pick something like negative 2, I will get a positive for that green factor. Remember, the yellow factor is always positive because it's squared, so f would be increasing on that interval. I'll pick a 0 next, and I get a positive. Now, that's as expected, because remember, negative 1 was not a critical value. So the first derivative should only potentially change signs at these critical values. I should have never expected the first derivative to change signs at negative 1. Negative 1 is not a critical value. So I'm expecting that. I'm also expecting to not see a sign change at 3 because 3 is squared. So on values on either side of 3, this particular yellow factor is not going to have a sign change. So I'm thinking this should still be positive, but I'll try something like 5. I'll get a positive times a positive. So I do have one spot where the first derivative changes signs. At negative 3, we are changing from decreasing to increasing for f. The first derivative goes from negative to positive, so this is a relative min right here when x is negative 3. Now I would want to find that output as well. I did this with a calculator earlier. You would want to be able to do it by hand. It's super annoying, but you could get there. But something close to 30. All right, the second derivative. And the factored form is going to be way more useful. Sometimes kids try to use the original form. Factored form is where you want to go. All right, so if I pick something to the left of negative 3, I will have a positive times a negative times another negative, which is positive. And so I will be concave up. If I pick something in between negative 3 and negative 1, such as negative 2, I will get a positive times a negative, which is a positive. We did not see a sign change for the second derivative at negative 3. We shouldn't have. It was not one of our possible points of inflection. The second derivative would only change signs potentially at 3 and negative 1. We should not have thought it would change signs at negative 3. It won't. So this is actually matching up properly. If I pick something next in between negative 1 and 3, such as 0, I will get a positive times a negative times a positive, which is a negative. I would expect to see a sign change there because that was a possible point of inflection where my second derivative equals 0. And then if I pick something like 5, I will get positive, positive, positive. And again, I would expect there to be a sign change here because of the fact that I am testing a possible point of inflection. How do you put this all together and create a graph from this? So what I'm going to do is I'm going to say I want the decreasing side of a concave up function. I want the increasing side of a concave up function. I want the increasing side of a concave down function. And I want the increasing side of a concave up function. So this will meet off where that one left off. It should look something like that. That's what I'm thinking it should look like. Now, where I have this sign change of the second derivative is a point of inflection. So there's a point of inflection when x is -1. And the output for that is -34.25. Good luck. And then we also had a sign change of the second derivative when x was 3. So that was another point of inflection at 3. And that's 29.75. Oh, I had the wrong value earlier. -3. I gave you the wrong output. -3 has an output of -78.25. Now I'm going to go and place these three important values. The relative min, -3, -78.25. I don't know, maybe here. That's going to be the lowest part in this local region. Point of inflection at -1, -34.25. So -1, -34.25. And I'm going to put this, I'm going to write it min. I'm going to write point of inflection and the ordered pair. Maybe I'll move this bad boy over a little bit to look more like -3. And then at +3 up to 29 point something, there's another point of inflection. And so now I'm going to try to put my little curves together. So this left side should be going downhill and concave up. And then I'm uphill and concave up. And now I'm going to be uphill, increasing but concave down. Now, a little hard to get my y-intercept in there accurately because this graph's not very accurate. Anyway, but maybe something like that. And then after that, I need to have a point of inflection and change to concave up instead of concave down. You might go like, where's the W here? Well, it is kind of a W. It's kind of a W. It's just this really warped one. And this is my sketch. Not a very scaled sketch, but nonetheless it is my sketch. The last part of our notes today, we're really working kind of more with that relationship between a graph, the first derivative, and the second derivative. And so here's a graph of f, and then we've got some questions about the first and second derivative from this graph. Now you actually have a solution already at the bottom of this page, but maybe don't look at it quite yet, like maybe cover it up or something. All right, we want to see where's the first derivative equal to 0. Well, the first derivative would be equal to 0 where we have those mountaintops and valleys, where we would have a horizontal tangent line. A little hard to tell where those x values would be. So these are approximate. I'll say -0.5, +1.5, +4.8. And so that would occur where f of x has a relative extrema. As long as those extrema are not where there are sharp turns, okay, because that would be where the first derivative is equal to 0. Spelling's hard, at least today. Okay. And now we want to know, where is the second derivative equal to 0? Well, the second derivative would be equal to 0 where we have a change in concavity. So I'm going to try to find out where those points of inflections are. And so I'm concave up. Somewhere in here, I'm switching to concave down. Now, where is that exactly? I don't know. I'm going to approximate this at 0.5. Someone else might say 0.7 or maybe even 1. So there would certainly be some grace given there. Now I'm concave down, and somewhere in here I start switching to be concave up. Where is that exactly? I don't know. I'm going to approximate that at 3.5. Someone else might differ. I might disagree with that a little bit, but there's concave up, and then I switch to concave down. And it looks to me like I'm concave up the rest of the graph. So I only see 2 spots where the concavity is changing. Be careful on this next one. I want where f prime is increasing. Whenever you see words increasing or decreasing, you are talking about the next derivative. This is asking us, where is the second derivative positive? That's really what this is asking us. We want where the first derivative has a positive slope. That's what increasing would look like. So that's where the second derivative is greater than 0. Well, the second derivative is greater than 0 where f is concave up. So f is concave up from, looks like negative infinity, according to my guess, about 0.5. And then again from around 3.5 to infinity. These are all intervals for x. Okay, these are x values only. I'm not giving any values here for y. When I want to find out where f prime is decreasing, that word decreasing is talking about the rate of change of f prime. This is talking about the second derivative having a negative sign. And this is where f is concave down. And so that's going to be from 0.5 to 3.5, approximately, right? I don't know exactly where those points of inflection are occurring. I want to draw a graph of f prime on the same coordinate system as f, as the last part here. Well, I'm going to really start by paying attention to where did I say that the first derivative had zeros. The first derivative we said had zeros where f had extrema. Okay, so f, I'm going to keep blue. I'm going to write f prime in like a purple color. Well, I'm starting off, as I go from left to right, where where f is decreasing. What that would mean is that f prime would have slopes that are below the x-axis. Then f turns and increases. So I should have positive slopes. However, these positive slopes can't just be positive forever because they've got to get back down to 0 right here, and this should be a smooth continuous function. So I'm going to say that it goes up, and then at some point it goes down. Now where it goes down, where that point of inflection is going to be the extrema of the first derivative. Points of inflection of f are going to be extrema from f prime. That might seem a little bit weird, but it's because it's where f prime changes from increasing to decreasing. And that would look like an extrema on f prime. That would look like a concavity change on f. After this relative max on f, after that, f is decreasing until we get to around 4.8. Now it's decreasing, but it's got to get back up to that height of 0 here that we already placed. So it's going to go down and come back up again. People get really stressed, like, how do you know how far down this goes? How do you know how far up this goes? I don't. I don't. Don't worry about it. It just needs to go down and back up again. And wherever that point of inflection was, wherever we thought that point of inflection was, that should, for f, that should be an extrema on f prime. It should line up. And after that relative